One. All right, today we're going to look at the substitution rule. Because of the fundamental theorem, it's important to be able to find antiderivatives, but our antidifferentiation formulas don't tell us how to evaluate integrals such as the integral of 2x times the square root of 1 plus x squared dx. The problem here is we can't distribute the 2x inside the radical. I suppose we could, but it's ugly. So to find this integral, we'll use the problem-solving strategy of introducing something extra. And here's the something extra, a new variable. We change the variable x to a new variable u. Suppose that we let u be the quantity under the root sign. So we're going to let u equal the 1 plus x squared. All right, that's fine. But now you have to take the derivative of both sides. So if we differentiate, we'll get du is equal to 2x. All right, so now notice that dx in the notation for an integral were to be interpreted as a differential. Then the differential 2x dx would occur u, and so formally, without justifying our calculations, we could write the integral of 2x times the square root of 1 plus x squared dx. Let's move the 2x over to the dx so it matches our du. So we're going to replace this with du, and then we're going to put the u in for 1 plus x squared, and we take care of a bunch of ugly here, and we make it look really nice. All we have to do is integrate the square root of u du. Well, we've done this. That's we go to the 1/2, add 1, make it 3/2, divide by 3/2 or multiply by its reciprocal 2/3, and add a c to it. And we are not done. We're not done because we have to have our answer written in terms of x. Okay, let's go grab that u again. It was 1 plus x squared. Let's put it in for u. We're going to need parentheses here. So that's 2/3 times our binomial, in parentheses, 1 plus x squared, all to the 3/2 power plus c. And we call it done. In general, this method works whenever we have an integral that we can write in the form of f of gx times g prime of x d. Wait a minute. I know this. That is the chain rule. So integration by substitution is like the chain rule for integration. Like the chain rule we had for derivatives, U-substitution will kind of like take care of the chain rule for integration. So if we let u equal g of x, that's the inner function, and du equals the derivative of the inside function times dx, then this notation here becomes f of u du, and that takes care of the chain rule. Now, one thing that a lot of teachers neglect to tell you, but to look for a pattern here, and that pattern is that your g of x on the inside is going to be 1 degree larger than the g prime of x on the outside, because if you take the derivative of that x term, you know you're going to reduce it by 1. So if you find big power on the inside, smaller power on the outside, that's usually a good indication, hey, let's do a U-substitution. All right, so a couple examples here. We want to evaluate the integral of x squared plus 1, all that squared, times 2x dx. In the past, what we would have to do is FOIL this out, distribute the 2x. Now, it could be worse. Oh, what if that was to the 4th or 5th power? We're going to be foiling till the cows come home. So, but now notice that on the inside of my parentheses, it's x squared, and on the outside, it's x to the 1st. A good indication for U-substitution. Let u equal the x squared plus 1. Now let's take the derivative of both sides. du is 2x times dx. That's exactly what we have. We make our substitutions with the u, and we're integrating u squared du. So something that looked really super ugly with all that foiling becomes very simple. That becomes u to the 3rd over 3 plus c. But we're not done, because we got to get this written back in terms of x. So we bring the x squared plus 1 back in for u, raise it to the 3rd power over 3 plus c. Now we're done. Oh, let's see. Oh, here we go. We have integrate x to the third cosine of x to the fourth. Oh, look, notice one power bigger than what's on the outside, plus 2 dx. So this is the inner function. That's going to be my u. Then du is going to be 4x to the third dx. And again, x to the third moved over to, wait a minute, we're short of 4. That's okay. All right, because we can multiply this by a 4 as long as we also multiply it by a fourth. So if we multiply, let's say, the inside by 4 and then the outside by 1/4, that will cancel each other out. But then again, all of this becomes your du. So now it's 1/4 times the integral of cosine u du. So we can integrate that. Or here's another technique. This is the technique I like to do. I like to just solve and get, if I need x to the third dx, that's all I want. So I divide over the 4, and I put in 1/4 du. Okay, well, as we all know, anytime you have a scalar multiple in here, or a scalar factor, you just factor it out to the front, and that's what you have right there. So it's 6 of 1/2 dozen the other. They both work really well. You choose which one you want to do. So now we integrate, oops, going a little too fast here. Cosine of u is sine of u plus c. Then we bring back in our x to the fourth plus 2, back for the u on the inside of our sine, and we are done. Part C. Well, here we got the square root of 2x plus 1. Well, that's x to the first. Well, a power less than that is x to the 0, or a constant 1. There's a 1 in front of my dx. So we'll let u equal 2x plus 1. Du, the derivative of both sides, is going to be 2 times dx. Okay, well, we can multiply by 2 and then multiply by half, or just divide over the 2 and then take the 1/2 out in front and integrate the square root of u du. And as we've done in the past, we put u to the 1/2, then we're going to add 1, which is 3/2, then divide by 3/2 or multiply by 2/3. All right, so 1/2 that's already out there times the 2/3, that's going to become 1/3 u to the 3/2 power plus c. Substitute back in your 2x plus 1, and we could leave it like this, or if you wanted to, you could change it back into a radical. The 2 in the denominator of the root is the square root, and the 2x plus 1 all raised to the third power. That's the top power in the fraction. Okay. Oh, the d. Let's come back here, mouse. Integrate x over the square root of 1 minus 4x squared dx. So again, inside my square root, I see an x squared. On the outside, I see x to the first. Therefore, 1 minus 4x squared is my u. My du is going to be -8, bring down the 2, times the -4 is -8x times dx. Well, I have the x times dx. Divide over the -8, makes it -1/8 times du. And now we'll make our substitution. Du will go on the top, or 1 over the square root of u, with the -1/8 out in front. Now, I really don't want the u to the 1/2 power in the denominator. Let's move it up to the top so we can use our power rule. Add 1, which gives me 1/2. We divide by 1/2. But dividing by 1/2 is the same as multiplying by the reciprocal of that, which is 2. So 2 goes into 8. This becomes -1/4. U to the 1/2 power. Bring back the 1 minus 4x squared inside of our square root for the 1/2 power, and it's now integrated. Part E. We integrate e to the 5x. Wait a minute. E to the x is just e to the x, but we never had a 5 here before. So maybe we better call 5x your u, because I'd rather have like e to the x, just one variable, so I want e to the u. So u is going to be 5x. Take the derivative of both sides, du would equal just 5 times dx. That's okay. Divide over the 5, make it 1/5 times du, so there's your dx. And now we'll integrate 1/5. Like I said, we'll move that out to the front, times the integral e to the u du. Well, e to the u, our rule says that's just e to the u plus c. All right, so our 1/5 times e to the u plus c is good. Wait a minute, we're not done. We bring 5x back in for u, and there's our answer. E to the 5x over 5 plus c. Whoo-wee. We're going to integrate sine squared 3x cosine 3x dx. Whew. Well, let's see. Sine is the bigger power. Cosine is technically to the first power. So I would say let's go with u equaling sine of 3x. And that way, if we take the derivative of both sides, we're going to get du. And the derivative of sine is cosine of 3x. But then chain rule, you got to take the derivative of the inside of our 3x, which is 3. So we multiply that to the front. So we don't have the 3 up here, so that's okay. We'll just divide it over here. So 1/3 times du equals cosine of 3x dx. So here's your du times 1/3, which we'll factor out to the front. So 1/3 times the integral u squared du. Okay, well, we can integrate that. That's going to be u cubed over 3 times a third. That makes it u cubed over 9. And then we can go back and bring our sine of 3x back in to u. So we cubed that. So that becomes sine cubed 3x plus c. Oh boy. Well, let's see here. Again, because cosine is to the third power, I'm going to let that be my u. And then the derivative of cosine, that's negative sine x dx. So that's that -1 there that we're going to have to divide over to the other side. Or if we could say multiply it to both sides. It's 6 of one, half dozen of the other. And so sine of x dx, that's the top. And then we'll put u in for cosine of x. So that turns out to u cubed on the bottom. But the -1 has to go out in front of our integral. Well, we need that u to the third power to be up in the top, so we can use our power rule. So we'll make it u to the -3. So we add 1, which is -2, divide by -2. Wait a minute. -1 times the -2. I'll change it to a +2 on the bottom. And then we can probably move our u squared to the bottom. Yeah, there we go, plus c at the end. And now let's bring our cosine of x back in. So 1/2 cosine squared x plus c. Oh, wait a minute, we could go even one step further. 1/cosine is secant. So 1/cosine squared would be secant squared. So we can call this 1/2 secant squared x plus c. And now we have it completely simplified. All right, h. Oh boy, integral tangent of x dx. Let's see. Well, the derivative tangent of x, that's secant squared x, but we don't have any secant squared x's up here, so I think we're going to have to throw that out. Erase. Well, what else can we do with tangent of x? Well, we could change it to sine of x over cosine of x. Well, I guess, well, we could try u being sine of x, but then my derivative is cosine x dx, and my cosine x is in the denominator, technically being divided into the dx, not multiplied. No, that's not good. Let's switch it around. Let's make this cosine x my u. And then the derivative would be negative sine of x times dx, and that's what's happening here, sine of x times dx. We just got to move the negative over with the du, so negative goes in front of my integral. 1/u du, well, we know what the integral of 1/u is. That's the natural log of the absolute value of u, plus our c. Then we can put our cosine of x into those parentheses. Now here, we don't know if our cosine of x answer is going to be positive or negative, so we have to keep the absolute value bars around that cosine of x for this answer. So we are now done. Example 2. Whoa, wait a minute. I have 2x to the first power on the inside, and I got x to the first power on the outside. These have the same powers. We're going to probably have to do some manipulation here. Let's see. I'm going to still let u equal my 2x minus 1. And I'm going to take the derivative of both sides. So du will equal just 2 times dx. Okay, so there's the dx. We're going to have to divide over the 2. 1/2 times du dx. So I make the substitution. 1/2 goes in front of my integral. But I don't have anything to do with that x there yet. Times the square root of u du. Oh, right here. I overlooked it. U is equal to 2x minus 1. How about we take what we let u equal and solve it for x? So we'll add over the 1, divide by 2, and we'll take u plus 1 over 2 and put it right there for that x. And now everything in my integral is now written with the variable u. Okay, let's see. What are we going to have to do here? I think what we should probably do is factor out this 2, because it's technically a scalar factor. So we factor out 1/2, multiply this 1/2, makes it 1/4. And so I got u plus 1 times the square root of u, so we can distribute that square root of u to the inside. So u to the first times u to the 1/2, multiply like bases, you add your exponents, so 1 plus 1/2 is 3/2, and then the square root of u times 1 is u to the 1/2 power. Well, I can integrate this, just use the power rule. Add 1 to 3/2, that's 5/2. Divide by 5/2 or multiply by its reciprocal 2/5. Add, like we've done before, 1 to the 1/2 gives us 3/2. Divide by 3/2 is the same as multiplying by 2/3 times u to the 3/2. We'll multiply everything by the 1/4, so we'll now distribute that. So let's see. Well, 2 and the 4 will cancel, so that should give me 1/10 u to the 5/2. And then 2 cancel 4, and then 1/6 u to the 3/2 plus c. And don't forget, we're not done, because now we have to bring, let's see, what did we let u equal? 2x minus 1. We have to bring that back in, put in parentheses. Those are going to be binomials for our 2x minus 1, raised to the 5/2 power, raised to the 3/2 power. And I think we can leave that just the way it is. We don't need to try to convert that back into radicals or anything. We'll just call it good. Part B of example 2. Oh, this one's even more weird. Here we have x squared on the inside, looking for x to the first on the outside, but we have x to the 5th. Still do a u-sub. Let's see what happens. Take the derivative of that. That's going to be du equals 2x times dx. Well, I have an x, but I've got x to the 4th left over. Well, we'll divide over the 2, substitute it in. So I broke x to the 5th down to x to the 4th times x dx, so I had that part. Hey, why don't we do the same thing as before? Here's x squared. We can take x to the 4th and break that down as x squared squared. Right? There we go. And then if we square the u minus 1 after we get the x squared by itself, we can substitute that in for x to the 4th. So I now have 1/2 times the integral. The square root of u, well, wait a minute. We can call that u to the 1/2. We'll probably have to FOIL out our u minus 1 squared. And so we get u squared minus 2u plus 1, distribute the u to the 1/2. So that's going to be u to the 5/2 minus 2u to the 3/2 plus a u to the 1/2. All times du. Okay, 3 power rules here. So 5/2 plus 1 is 7/2. Flip that to 2/7 times u to the 7/2. 3/2 plus 1 is 5/2. Flip it to 2/5 times 2 is going to be 4/5. U times 5/2. Add 1, that's going to be 3/2. flip that 2/3 multiplied to that u, so that's 2/3 u to the 3/2 power plus c. We could leave it like that, and we can distribute into 1/2, which might not be a bad idea because then this denominator of 2 can cancel into the 2 for 2 of our numerator, so let's do that. So that gives us 1/7 u to the 7/2 minus 2/5 u to the 5/2 plus 1/3 u to the 3/2 plus c. Now, then we take our u, which was 1 plus x squared, bring that back down, substitute them in as binomials for all the u's, and now we're done. So we saw in A, the powers were the same in and inside, outside, and now here the outside's bigger than the inside, but we're hoping that we can break it down and still use what we let u be equal to somehow substitute and replace it. Definite integrals. When evaluating a definite integral by substitution, two methods are possible. One method is to evaluate the indefinite integral first and then use fundamental theorem. Another method, which is usually preferable because it cuts down on the work, is to change the limits of the integration with the variable that you're changing it to. All right, so the substitution rule for a definite integral means if g prime is continuous on our interval from a to b and f is continuous on the range of u equals g of x, then when you put in your u for g of x, you take your a, substitute it in for for x into g of x, and that becomes your lower bound. Plug b into x for g of x, and that becomes your upper bound. And then when you integrate this with u, we'll just evaluate by plugging in those values into the u, and then we're done. We don't have to bring back what the u ugliness was. So here's an example. From 0 to 4, square root of 2x plus 1. I think we did this before, but we didn't have the boundaries. So remember, we let u equal 2x plus 1. All right, now we're going to let 4, that's our upper bound, plug it in. 2 times 4 is 8 plus 1 is 9. That's the upper bound. Then put in the 0. 2 times 0 is 0 plus 1 is 1. So your du is equal to 2 times dx. And you can do these in any order. Once you got the u, you might as well keep working with it. So now, divide over the 2, 1/2 du dx. So now we're going to integrate 1/2 times the integral, lower bound 1 to upper bound 9 for when we have a u in here. And that's u to the 1/2 power times du, because again, square root changes to a 1/2 power. Add 1, 3/2, multiply by 2/3. We're going to evaluate that from 9 to 1. We don't want to put in the 2/3, so let's multiply it to the 1/2, so we'll call that 1/3. So 1/3. Now we put the 9 in for the u, 9 to the 3/2. We put 1 in for u, so 1/3 times 1 to the 3/2. Well, I'll do the more difficult one. 1 to the 3/2, that's just 1, times the third, that's just minus 1/3. All right, here, let's see, 9 could become 3 squared, which cancels the denominator of 2 in my power. So that's 27. 27 times the third will be 9. So this is going to be 27 thirds, which is 9 minus 1/3. Or we can leave this as 27 over 3 minus a third because they're common denominators, which is a good idea to do. Subtract, we get 26 over 3, and there's our answer. If you did it by the first method, you would have to bring the 2x plus 1 back in, and then you'd have to work with that bigger mess inside of that 3/2 power. All right, so let's try this one. B says we're going to integrate from 0 to 1 of x times the binomial x squared plus 1 to the 3rd power. Perfect u sub here. U is going to be the x squared plus 1. All right, let's change our boundaries. Plug in the upper bound of 1. 1 squared is 1 plus 1 is 2. Plug in the 0 squared plus 1 is 1. So there's your new boundaries, upper and lower. Du would be just the 2x dx. Well, we don't have a 2 here, so again, divide over the 2. 1/2 times our integral. We're going to integrate with these new boundaries from 1 to 2 of u cubed du. All right, so that's going to be add 1, 4, divide by 4. U to the 4th divided by 4. And then we're going to multiply this 1/2 to this, so that can become u to the 4th over 8. So 2 to the 4th over 8 minus 1 to the 4th over 8. And again, don't simplify this. This is 16 over 8 minus 1 over 8. You've got common denominators. Just go ahead and subtract your numerators. 15 over 8 is our answer. C. X to the first on the inside, constant 1 dx on the outside, perfect u sub. U equals 3 minus 5x. Okay, change our boundaries, plug in the 2. That's 3 minus 5 times 2, which is, that's -7. 1 gets plugged in, that's going to be 3 minus 5 is -2. This is a little different. Upper bound is -7, lower bound's -2. Technically, the lower bound's actually bigger than the upper bound. So we can take our du over dx, and dx, so that's -5, divide over our -5 to the du, make our substitutions, and you can actually leave those numbers as is. Nothing wrong with it. You could, if you wanted, to have the bigger number on top, smaller on the bottom, then take this, multiply it by a negative, which would change this to a positive 1/5. 6 of one, half dozen of the other. If you forget to do that, that's no big deal. It'll still work. So let's see, power rule, add 1 to -2. That makes it -1, divide by -1. Okay, and then we'll evaluate it from the -2 up to the -7. So here we have a negative and a negative, which is going to change this to a positive anyhow. The u to the -1 is going to come to the bottom, so we have 1 over 5u. Okay, let's plug this in. So we got 1 over -35 minus 1 over -10. Well, minus the negative, because it's going to change that to plus 1/10. And we need common denominators, so that would be a 70. So this will be -2 over 70 plus 7 over 70, and that would be 5 over 70, which reduces to 1 over 14. All right, D. Integrate from 1 to e, natural log of x over x. Whoa. Oh, wait a minute. I see it. I'm going to I got it. The derivative of ln of x is 1 over x. So let's let u be the natural log of x. And then let's change our boundaries. Natural log of e is 1, so that's the upper boundary for u. Put in a 1. Natural log of 1 is 0, so we're going to go from 0 to 1. And like I said, the derivative of the ln of x is 1 over x, so that's this x in the denominator. So we can just integrate this from 0 to 1 of u times du. So this becomes add 1, u squared over 2. So we put in the 1, so that's 1/2 minus 0, which equals 1/2. Something looked ugly, we made it look better. And that's the end of the U substitutions.